Shifts. That's right. Today we're going to be going over chemical shifts with NMR spectra. We've already done integration and we understand what non-equivalent protons look like. We are now going to move on to chemical shifts. This is going to tell us a lot of information about the environment around the atom that we're looking at. What is bound to that atom? What kind of groups does it have bound? Electron withdrawing or electron donating groups? And where does this signal now take place in the NMR? Here I have three compounds: diiodomethane, dibromomethane, and dichloromethane. As you can see, they all have different chemical shifts. The way I know they have different chemical shifts is what we've talked about before with parts per million here in the bottom. Our diiodomethane is at the lowest ppm and our dichloromethane is at the highest ppm. Here on the right, I have listed the Pauling electronegativity scale for the different halides. As you can see, of the three compounds that we have, chloro is the most electronegative, and we know this from our other chemistry courses. The most electronegative atom here has shifted this CH2 group to a higher ppm. I should note that we know we're only going to get one signal for each of these compounds. We know this from our last video of the substitution test. So again, diiodo has one signal here. It's at the lowest ppm. Then we have our signal for our two hydrogens for the dibromo. And then the highest ppm is the one with the dichloromethane. Now, when we look at this, the way we would describe it as organic chemists is that this is shifted downfield. And if it shifts to lower ppm, we would consider this shift to be upfield. This is how we compare different compounds. Now, what is happening here is that our chlorine is the most electronegative atom of the three compounds. This is withdrawing electron density away from this CH2. More so than our bromine and more so than our iodine. So this is the most electron withdrawing. I'll put G for group, most electron withdrawing group. It's a withdrawing electron density the most. And so in this case, what happens is we call this de-shielding. These hydrogens are de-shielded is what we like to call it. What I like to do is think about electrons around a nucleus as a shield against the external magnetic field that we're applying. Iodine is less electron withdrawing. Anytime you have an upfield shift, you would say that this signal, the atoms for this signal are more shielded. They have more electron density around that atom, which shields it from the external magnetic field. Let's go back to our original example of ethyl bromide. In this case, we could easily tell which signal corresponded to which set of chemically inequivalent protons. So in this case, we had 2 protons to 3 protons for the ethyl bromide. We can also determine this based on what we just learned in our previous slide. Our protons for A, this CH2, are bound directly to a carbon that's bound to a bromine, which is an electronegative, electron withdrawing group, electronegative atom. This would make sense then that the CH2 compared to this methyl is shifted downfield. This CH2 is de-shielded because of its close proximity to that bromine. So here we could also determine the 2 signals and what they correspond to on ethyl bromide. So here we could determine that HA is the most downfield signal. Downfield is also the higher ppm. Remember, it's going here to the left, so higher ppm, because it is nearby that bromine. And then here, HB would be these 3 protons. So again, we could determine this with our integration, but if you didn't know the integration, you could still determine which signal corresponded to which set of protons. Here I'm showing you a table from your appendix that you'll be using for all of your exams. This is the same table that's also in the appendix for your Chem 344 class. Some of you are taking that class as well, and most of you will be taking that maybe next semester. I like to use the same one to make it easier on you. So this here is showing our proton signals and the ranges in which we would expect to see them. What you're going to notice is that let's just start here with our saturated CH bond, sp3 CH bond, completely saturated. This would be reminiscent of our CH3 group on our ethyl bromide. Now let's find where we can, let's find a CH that would have an electron withdrawing group, or this halide. Here we have an X. So this range here is corresponding to the CH2 group that we're looking at. As we can see, it would take place between about 2.5 and about 5 ppm. It's quite a range here. But what I want you to notice is that the range of a hydrogen on a carbon directly attached to a halide is higher ppm than a hydrogen bound to a saturated alkyl chain. So in this case, our last example, based on this graph, we would expect this CH2 to be shifted downfield. Let's double check. Our signal here is around 1.7 for our CH3, and then the signal here is around 3.4. Does 1.7 fit in this range? It absolutely does. So you can see here the range is about from 1 to about 2 ppm. And then our other signal was around 3.4. That was for this CH2. And it is indeed within that range. So this is a really good way that we can check to see if what we were thinking is correct. Here's another example. Let's look at methyl acetate. We have a methyl group that is attached directly to a carbonyl, and then we have a methyl group that's attached directly to our oxygen. My first question is, are the two methyl groups equivalent? Are they going to have the same signal in our proton NMR? What do you think? Well, we don't have any symmetry, right? There's no symmetry in this molecule. Therefore, these two methyl groups would show up as two different signals. All right, so we know they show up as two different signals. They both have 3 hydrogens. Here I'm showing the proton NMR. Now my question is, which signal corresponds to which methyl group? Now would be a great time for you to pause the video, go back to our graph on the previous slide, and see if you can figure out which methyl group corresponds to each signal. Okay, let's go through this. We know that one of our methyl groups is bound to a carbonyl, and one of them is bound to an oxygen. Okay, let's see if we can find these two fragments in our table from our appendix. Let's look for a hydrogen bound to a carbon that's bound to a carbonyl. Let's find this first. If you found it here, you are correct. It is right here. The range is a little higher than we would expect for a fully saturated alkyl chain, which makes sense because carbonyls are electron withdrawing. What about the hydrogen bound to a carbon directly bound to an oxygen? Our OMe group is right here. So as you can see, our OMe group is going to be shifted more downfield than our methyl group that's bound to a carbonyl. Based on this appendix, it's clear the range for the methyl group bound to an oxygen. Those hydrogens are going to be shifted to higher ppm or downfield. This makes sense. We know oxygen is electronegative. It's an electron withdrawing group. It's electronegative. It's going to withdraw electron density through the sigma bonds, and the hydrogen, our proton, is going to be de-shielded. Our proton is going to be de-shielded, so it will have a higher ppm. So in this case, our methyl, let's label the methyl here A, and a hydrogen's here on B. So our OMe group we know is shifted the most downfield. So this will be HB. This will be HA. Let's look at this just with resonance as well. Here we have our oxygen of our ester. We're going to push the electrons up. See where the electrons are moving. As you can see, the oxygen of the OMe group has a formal positive charge in our resonance structure. This is very electron withdrawing. So by resonance, that's another way we can look at this to make sure that what we're thinking is in fact reasonable for our proton NMR. Let's talk about another topic in NMR. One of the things you might have noticed in this appendix is that our benzene shifts pretty far downfield compared to, say, a saturated alkyl group. They're typically in the range of around 6.5 to 8 ppm. The range depends a lot on the functional groups that we have bound to that aromatic ring. Benzene is at 7.34 ppm. And just as a note, chloroform, which is a solvent we use a lot in our NMRs, appears at 7.2 ppm. So it's interesting that benzene would shift these CH bonds on benzene. These hydrogens would be shifted so far downfield. There's no major electron withdrawing group on it. So what's happening here? Aromatic rings are strongly de-shielded due to an induced ring current in the ring. Remember the external magnetic field. Remember our instrument, and then we've got external magnetic field. We're being applied to the molecule. With benzene, there is this induced ring current, and I'll depict it here simply. This induced ring current is what causes this extra de-shielding on the hydrogens. Our protons here are de-shielded. So remember our external magnetic field is going this way. The ring current is going against the field on the inside of this ring. However, it's going with the field. Notice how this is going with the field on the outside of the ring. So it de-shields the exterior of the ring. So the protons attached to an aromatic ring are de-shielded. They feel the force of the external field greater than on the inside, but there are no protons on the inside. Let's look at an aromatic example. Here again, I have that shielded is upfield and then de-shielded is downfield. Let's figure out the signals that we have here. Which signal corresponds to which hydrogen in this molecule, paraxylene? You can go back and use your appendix and see if you can find the ranges for the CH bonds that you're looking at. The methyls here for paraxylene, will they be lower in ppm or higher in ppm than the CH bonds, the protons here, B, on the aromatic ring? That's what we're trying to figure out here. Well, based on what we've learned from the appendix, it's clear that the CH bonds are going to be shifted downfield compared to an aliphatic CH. Another way you can see this Look here at our integration. We have 6 to 4. Paraxylene, we know, we can see the symmetry that we have here. The methyls are equivalent. That's why we have A and A. And I should just note here, these two hydrogens are equivalent, and the hydrogens across this plane of symmetry are also equivalent. So that's why we have a signal of 4 hydrogens. So our integration could help us with this. We know that we have 4 aromatic hydrogens, that would be HB, and then we have 6 aliphatic, which would be HA. But let's just make sure that makes sense with our knowledge of chemical shifts with aliphatic versus aromatic region. And it does. The aliphatic region, this makes sense that it would be at a much lower ppm than the aromatic. Our aromatic region here, paraxylene CH bonds are occurring just a little above 7, which is right in the range that we've talked about. Let's do another example. 1,4-dimethoxybenzene. We've seen this methoxy group in an alkyl group before, not attached to a benzene ring, but we've seen this before. Our CH3 here is equivalent to this CH3. There is a plane of symmetry. There's also a plane of symmetry this way. This makes sense why we have 2 signals. 6 hydrogen and then another signal of 4 hydrogen. And we know that our methyl groups would be the lowest ppm signal here. So this, let's label these with HA. And let's label our aromatic hydrogens as HB. Now, one thing that you'll notice is that these are in a different ppm than paraxylene. So what's going on here? Here's our paraxylene again. We have our methyls. Let's go here again. Let's do HA, and then we have B. So HA and HB. And for our 1,4-dimethoxybenzene, let's do our HA and HB. What do you notice? What do you notice about the difference between these 2 spectra? Let's look at HA. The 3 protons on HA from paraxylene to 1,4-dimethoxybenzene, how did they shift? They shifted downfield. They shifted to higher ppm. This means that they are more de-shielded. This makes sense. We've talked about how oxygen is an electron withdrawing group, and on our methyl acetate example. What about HB? HB in the aromatic region actually has an upfield shift. Interesting. Interesting. We just talked about how oxygen is electronegative. This seems opposite of what should happen. It's very interesting with an aromatic ring. This oxygen can be shown with resonance where when it's bound to an aromatic ring, it can actually donate electron density. This is why I love resonance. We can really describe a lot of things with this. In this case, when an oxygen is bound to an aromatic ring, it shows that our protons of the aromatic ring are more shielded. See the difference? Alkyl versus this aromatic ring. Now, at this point, you could use the Curfy-Morrison parameters to calculate all of these chemical shifts. I figure this is not an algebra course. I'd rather teach you the organic chemistry and the logic behind this so that if you don't have that table, you could still figure this out. Let's redrop 1,4-dimethoxybenzene. And what we're going to do is we're going to walk through the resonance. Now, initially, we talked about how oxygen is an electron withdrawing group. What if we did look at this as an electron withdrawing group? We have a double bond in our aromatic ring. We can push it to make a carbon-oxygen double bond. Here. This would be incorrect. Why is it incorrect? Well, when we look at this, how many electrons are around your oxygen? We have 3 bonds to it, so there's six electrons, and then there's 2 lone pairs. This puts 10 electrons around oxygen. I encourage you to practice resonance structures. We are going to use them a lot throughout the course, which is why I'm bringing them up now. 10 electrons, no go. Remember our octet rule from last semester? Don't do this. Let's do it again. Well, we can't pull electron density out of this aromatic ring. So what can we do? Well, we can try to push electron density in. Let's see if we can get a good resonance structure that way. So here I've got my lone pair. I'm going to push it into the aromatic ring. Once you make one arrow, the carbon just picked up a new bond, so it has to lose something. So that's why I draw the second arrow. What do we have from here? When I draw resonance structures, I always like to keep everything the same that wasn't touched by an arrow. Then I go in and I make sure I have everything right. It's the easiest way, I think, to make sure you're not missing anything. I will make mistakes. We all do. We're human. All right, here is my first resonance structure. As you can see, one of the carbons has a formal negative charge. Now, we talked about 1,4-dimethoxybenzene shielding the aromatic protons. Can you see with this resonance structure how the methoxy group is shielding that hydrogen? On the carbon, there's a formal negative charge, so there's more electron density around it. That's why it's shielded from the magnet. Let's go through and write the rest of our resonance structures. Push these electrons down, and then I'm going to put the electrons here on the carbon that's bound to the oxygen. And this double bond didn't move. All right, let's draw one more resonance structure. Okay, and then we can draw one more to get us back to our major resonance structure, which is the one that was drawn originally. And here it is, fully aromatic, a very happy compound. And there you have it. We show that an OMe group on an aromatic ring donates electron density. So it shields these aromatic protons. More electron density, more shielding. Think about that shield of electrons, and that's going to shift it to lower ppm. All right, let's add another one to this equation. Here's our paraxylene. We know our methyl group here in blue. These 6 protons in this signal around 2.25, and then B is here around a little above 7. We know 1,4-dimethoxybenzene has the methyl groups that is shifted how? Downfield. I'll draw this in red. And then our protons on our aromatic ring are shifted upfield slightly. This will be B in red. What about 1,4-diacetylbenzene? We have a methyl, and then we have our CH bonds. This also has symmetry. We're going to have 2 signals. Our CH groups are equivalent. We'll have 1 signal of 6H and a second signal of 4H for our aromatic ring. Where do you think that these will happen? Now would be a great time to pause the video and think about where you imagine these signals will be shifted. All right, our methyl groups are shifted where? They're shifted downfield, okay, compared to paraxylene. We're comparing these to paraxylene. So we will label these are HA and these will be HB. This is in a light blue, okay? Make this light blue for you. So our HA is shifted downfield to paraxylene. This makes sense. We've seen methyl acetate, and we saw that the carbonyl is electron withdrawing. However, it's not as electron withdrawing as what happened with our methoxy group. Okay, what about the aromatic region? What does the carbonyl do to the aromatic region? Think about the resonance. Shifted it where? From paraxylene? Shifted it more downfield. Downfield. That means that these protons are de-shielded. Why is that? Carbonyl is de-shielding those CH bonds. You might have guessed it. We are going to do more resonance. Again, you could calculate the Curfy-Morrison parameters and you could figure out the expected chemical shift, but I'd really like for you to also understand the resonance. Again, we'll use this so much in our course. I like to introduce it now. 1,4-diacetylbenzene. We talked about how it shifted the CH bonds, or the protons on the aromatic ring, it shifted them downfield. And why is that? Let's see if we can draw a reasonable resonance structure that shows electron density being removed from the ring. Again, for a resonance structure, I'd just like to draw everything that didn't change. Here's our first resonance structure. Let's continue with this. What are you noticing different about this resonance structure? We're going to talk about this compared to our methoxy example. Okay, and we can draw another resonance structure here. Notice how we're using a 2-ended arrow for all of these arrows because we are indeed moving 2 electrons. And then one more. We're going to take our negative charge on our oxygen, we're going to push it down, and then we're going to push the electrons from the double bond to reform our aromatic ring. This is our most stable form, our most stable resonance structure. A resonance structure is simply just telling us where do the electrons lie on this molecule? We draw them as if the double bonds are only here on the aromatic region. Resonance allows us to kind of understand how the carbonyl is talking with the aromatic ring and how the electrons really are spread out over the molecule. We simply draw it, but resonance really describes the full picture of the molecule. So as we look at this, one thing you'll notice is that in the aromatic ring, we have a positive charge on these carbons, a formal positive charge. Now, we could also go through and do the resonance using the other carbonyl, and you'll see that positive charges form on all of the carbons in this molecule. So you could go through and do that as well. What you're seeing is that the carbonyl withdraws electron density. From aromatic ring. So it de-shields these protons. If it de-shields the protons, then it has a higher ppm shift. Hopefully that makes sense. If it doesn't, now would be a good time to pause and go back and listen to this section again. I now want to go over carbon NMR. Uses a lot of the same ideas that we've gone over with proton NMR. There's just a few caveats. For proton NMR, for our paraxylene, how many signals did we have? We had 2. Proton NMR, we had 2 signals. For paraxylene, for the carbon, how many signals do you see? We see 3 signals. Why is this? Well, we didn't change our symmetry, right? We still have symmetry here. So that means that this methyl is the same as this methyl, okay? Our aromatic carbons are still the same. This carbon, this carbon, this carbon, and this carbon are indeed the same. There's something else that's different about carbon in that we can see the atoms that don't have the hydrogens, right? We're doing carbon NMR. We can't forget about these 2, right? Let me redraw this. So for paraxylene, let's label this. Our carbons of our methyl groups, why don't we label this with A? The carbons in the aromatic ring that we know are equivalent are B. And we have one more type of carbon environment. We have a carbon that has no hydrogens, right? We're going to say this is C. And in this case, we show that there should be 3 signals. One thing you'll note is the chemical shift is also very apparent in the carbon NMR. A is the lowest ppm shift here in this NMR. Our next signal is for B, and then our final signal is on C. Many times on an exam, you won't be able to distinguish between C and B or different carbons in an aromatic ring. Paraxylene doesn't have anything that is shifting those carbons much. It just has methyl groups. One thing you will notice, though, is that B is much higher. It is more intense of a signal than C. This tends to happen for a couple reasons. One of the reasons in this case is simply because we have more of carbon B, okay? This wouldn't be something you would use as an indicator, though. There's something else we're going to use instead. The chemical shifts. This is our table from our appendix, and I just want to review this. One thing you'll notice about this table is that we discuss sp2 versus sp and then sp3 hybridized carbons. What you'll see is that an sp3 hybridized carbon, like alkyl chains, are lower ppm than anything that is aromatic or that has an alkene. Alkynes are weird. They're in the middle, and they range over the sp2 and the sp3 ranges. Let's go back to our paraxylene. And in this case, What I would be asking you on an exam is I would like for you to use a proton NMR, an IR, and a carbon NMR to help explain how you knew that paraxylene was the compound that all three spectra line up to be. And what you would do, typically what I like to ask here is that I would be having you label this as an sp3 carbon. And I would want you to know that these two are sp2 hybridized carbons. Let's do one more example with paraxylene with our carbon NMR. Again, we know this is our A, here's B, and here's C. What about the dimethoxy benzene? Where is this going to show up on a carbon NMR? Now would be a great time for you to pause the video and think about where you expect to see these signals. Think about our resonance that we talked about. We know that the 1,4-dimethoxybenzene has the same symmetry that we've discussed with paraxylene. We expect there to be 3 different signals, 3 different carbon atoms. Our signal for our methyl group here, let me write this in red, is here. Notice, how did it shift? It shifted downfield. The carbon is bound to an oxygen. Same thing as our proton NMR. What about our carbon in the aromatic ring, our B, our carbon B? Where does that show up? This is shifted upfield, right? It's shifted upfield. This makes sense because of the resonance we did for our proton spectra for this. Lastly, we have our carbon here. This is our C. This is shifted downfield. Let's see if we can figure this out with resonance. Again, one of the things that was different about the carbon NMR that may have been surprising is that our carbon here was shifted downfield when we had an OMe group on it, meaning it was de-shielded. Can you see in the resonance why that makes sense that that carbon is de-shielded compared to our paraxylene example? So if we have an OMe group rather than a methyl, that carbon circled in blue is de-shielded. Here in our resonance structure, you can see that this carbon is bound to an oxygen that has a formal positive charge throughout our resonance structures. That makes sense why that carbon has electron density withdrawn from it. And so that is the reason why that carbon is shifted downfield. I love using resonance for these questions because it helps you understand chemically what's happening. That's it for our chemical shifts. We not only did carbon, but we also did proton. The next topic we're going to talk about is splitting. This is what the signal looks like. As you could tell with our example from ethyl bromide, when we looked at this, you could see that the signals had other signals within them. We're going to talk about why we get certain signals, and that's going to tell us a lot more about what atom is bound to what atom in the next video.